Good day, everyone, and welcome back to the U.S. Department of Energy's Fuel Cell Technologies Office monthly webinar series. We've got a great presentation this month as Ahmad Mayas here at the National Renewable Energy Laboratory presents the fruits of his research efforts into manufacturing competitiveness and supply chain analyses for hydrogen refueling stations. My name is Chris Worth. I am a project monitor within the Fuel Cell Technologies Office and the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our EERE website in about 10 days. Be sure to check back to the site if you'd like to download a copy of the slides or watch the webinar recording. Next slide, please. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Next slide, please. With that, I would like to introduce my friend and DOE webinar host, Dr. Nancy Garland, joining us from the Department of Energy headquarters in Washington, D.C. Nancy is a technology manager within the Fuel Cell Technologies Office. It's a pleasure to have you with us, Nancy. Good afternoon.
Thank you, Chris. It's my pleasure to introduce our speaker today, Dr. Ahmad Mayas. Dr. Mayas is a clean energy systems analyst at the National Renewable Energy Lab, and he is currently involved in R&D activities of polymer electrolyte membrane, that's PEM, fuel cells, and water electrolysis. Dr. Mayas received a Master's of Science and a PhD in Automotive Engineering from Clemson University in Clemson, South Carolina. After graduation in 2012, he worked as a research fellow at the University of California at Berkeley and at Lawrence Berkeley National Lab, where he worked on developing techno-economic analysis for stationary fuel cells. Dr. Mayas has over 13 years of experience in advanced manufacturing analysis, including manufacturing of fuel cells and water electrolyzers, and he's authored and co-authored more than 50 journal publications and technical reports. So it's my pleasure to introduce Dr. Mayas, and he's going to talk to us about manufacturing competitiveness, supply chain analyses for hydrogen refueling stations. Ahmad?
Thank you so much. Thank you, Chris. Thank you, Nancy. So, hello, everybody. So, as Chris mentioned, the title of the presentation is about manufacturing competitiveness and supply chain analyses for hydrogen refueling stations. In terms of the agenda of this webinar, I'll start by giving you a brief introduction about different technologies of hydrogen stations and status of hydrogen refueling stations worldwide, and then move to discuss some findings about hydrogen refueling station capital cost in different countries. And one of our core analyses is manufacturing competitiveness analysis in different countries. And finally, we will wrap up this presentation by some concluding remarks and answering your questions if you have any. So, relevance and goals of this work. Actually, this work is funded by Fuel Cell Technologies Office, and the goal is to provide FCTO and other regulation agencies and experts involved in hydrogen infrastructure with a platform for manufacturing cost analysis for major components in the hydrogen station. And the ultimate goal is to identify potential cost reduction in manufacturing phase of major components like compressors, heat exchangers, dispensers, chillers, and storage vessels. And also to investigate effect of learning experience and availability of part suppliers on the final cost of hydrogen stations. We also did some analyses on supply chain mapping to assess international trade flows between different countries. So in terms of the approach, I would say that we have three main analyses here. The first one is manufacturing competitiveness analysis, or manufacturing cost model using minimum sustainable price, and I define minimum sustainable price when we reach this slide. So we started this analysis by collecting global and local assumptions by country in order to feed this to our cost model, and after that we got cost curves or results where we added other stuff to these cost curves to come up with minimum sustainable price. And we also get some cost numbers from previous studies and from some of our collaborators. So we benchmark our results with these studies. Another focus was on effect of some qualitative factors other than cost on determining the location of manufacturing facilities. Like, for example, what is the effect of availability of skilled labor in certain countries or regions on future decision of locating new manufacturing facility in that region. And the third analysis was focusing on supply chain map, where we developed detailed maps for international trade flows and like projections for hydrogen stations in the coming years. In terms of the key outputs, as I mentioned, manufacturing cost models and minimum sustainable prices, and international trade flows between different countries. And the final key output was estimation of future hydrogen refueling station technology costs and effect of these cost or these component costs on reducing hydrogen prices. As most of us know, there's like at least two architectures of hydrogen stations. The first one is depending on gaseous hydrogen, and the other one is depending on liquid hydrogen. Whether this being delivered hydrogen to the station or on-site production, this is not what we are focusing on at this project. So for gaseous hydrogen station, as you see, I mean, we assume that the hydrogen is delivered through tube trailers to the station and stored in intermediate pressure vessels, and we have compressor and chiller and heat exchanger in case if we want to dispense it at 70 megapascal, and we have dispenser where we can dispense hydrogen into a fuel cell electric vehicle tank. For liquid hydrogen station, it depends mainly on delivered hydrogen, and it can be hydrogen can be generated on site as well, and then stored in cryogenic form at around negative 253 degrees Celsius, and after that it can be pumped, and we need like to change the phase of liquid hydrogen to gaseous hydrogen before dispense it into fuel cell electric vehicle tank. Based on the data we collected, we found that majority, and what I mean by majority is 90% plus of past 11-10 years installations was of was gaseous hydrogen. So we focused on analysis or manufacturing competitiveness analysis for gaseous hydrogen in this project, and here are the major systems inside the gaseous hydrogen refueling stations. And as you see, I mean, we have 4 or 5 systems. So as you see, we have combustion system, storage system, dispensing system, and electrical system. And if we consider cooler and heat exchanger as an individual system, we will end up with 5 systems. And as you see, these parts with red asterisk are the parts we developed cost model for. So once we start talking about hydrogen infrastructure, this should be related in a way or another to a number of fuel cell electric vehicles on the roads. And these are like some snapshots from previous studies for the projections of fuel cell electric vehicles in the coming 15 years. And, you know, I mean, there is sort of discrepancy between these studies, but with the most conservative study, the estimate for 2020 sales or production is about 30,000 fuel cell electric vehicles worldwide. And for 2030, the estimate is more than 250,000 fuel cell vehicles produced at that year. In terms of international hydrogen refueling station status, so we collected data, and I just wanted to highlight this is, I would say this is like sort of dynamic map, because every day we hear like new news about like the future projections for hydrogen stations in different countries. So this map is based on the data we collected until December 2016, and this is the projections in different countries. And if you look at this map, you see the leading countries in this regard are United States and mainly California state. We also have Germany and Japan. And to a lesser extent, we have Scandinavian countries, United Kingdom, and South Korea. In terms of international trade flows, we collected data for installations in the past 11 years, starting from 2006 to end of 2016. And we plugged this data into this map. And as you see, this map is based on number of stations being manufactured and installed in different countries. So as you see, blue line is the country of origin or the exporter country, and it converts to green when it enters to the import country. And as you see, I mean, in terms of the thickness of the line gives you the indication about number of stations being shipped from or to that country. So if you look at these lines, you see that we have thicker lines in Europe, and this is mainly stations manufactured in Europe, mainly Germany, and then shipped to European countries. And there is a good number of stations being manufactured in Europe and shipped to United States. And same thing we have for United States, with a good number of stations being manufactured domestically in the United States and installed within United States borders. And Japan also has like good trade flows, and this is mainly between Japanese manufacturers and between installations in Japan. Okay, so another depiction of the same data. So what we are trying to do here is that instead of going off number of stations, because we found that about 2/3 of these stations are demonstration or small scale stations with less than 100 kilogram per day dispensing capacity of these stations, we decided to go with capacity by country, because it's more reflective in terms of like how this country is advancing in terms of hydrogen infrastructure. So if we look at these bars, you see we have 3 colors. So yellow is for domestic stations being manufactured and installed in the same country. Exported stations are represented by blue, and green represents imported stations. So if we look at different countries, you see United States and Germany are leading the globe in this regard, with a good number of stations being manufactured and installed in the United States, and a small number of stations being exported to other countries. And if we look at the German case, you see there's a good number of stations being manufactured and installed domestically in Germany, and another good number of stations being exported to other countries. In terms of international manufacturers, so I think this map is a bit denser than it should be, but I think if you need like to look at this map, you can access it at the link on the bottom of the slide. So the idea here is to give you an indication about clusters or the hubs where we have the manufacturers. So as you see, we have a good number of manufacturers in the East Coast in the United States, and another good number of manufacturers in Eastern Europe. And as you see, these manufacturers are classified in terms of hydrogen refueling station providers, pressure vessel manufacturers, compressor manufacturers, and dispenser manufacturers. Moving to discuss capital cost for hydrogen refueling stations in different countries. So we collected the data and we plugged it in this slide. And as you see, we have the cost broken down by individual components in the hydrogen refueling station. And as you see, we have, for example, the first two are from Europe and Japan, and the last two, the lower two stacked bar charts are for US market. And generally speaking, if you look at the data and the scales, you see that the cost or the capital cost of stations installed in Japan, roughly speaking, is 2 times the cost of stations being installed in Europe or United States. And this is mainly due to a number of factors, including safety regulations in Japan, because of the seismic effect in Japan. So their safety regulations are really stringent. And in terms of standardization or regulations of materials, Japan, for example, does not allow to use chrome molybdenum steel for storage vessels, which tend to be cheaper than stainless steel. And this is, chrome molybdenum steel is allowed to be used in United States and Europe. In terms of manufacturing of hydrogen refueling stations components, so here is an example for hydrogen compressor, and here are the assumptions we use to develop our cost model. So as you see, it's a single stage compressor with a compression ratio of 6:1 or less, and inlet pressure is around 200 bars, and it can deliver pressure up to 420 bars. And as you will see, we focused on manufacturing of compressor shell and internal parts only, and after that we added other parts for balance of system to come up with a final cost model for the compressor. And as I mentioned before, we use minimum sustainable price using WACC, and WACC stands for weighted average cost of capital. And the idea here is that every manufacturer, or theoretically speaking, most of the manufacturers have equity and debt ratio. And if the debt ratio increases over the equity ratio, that means that manufacturer needs to generate more internal rates to cover the debt service. And this means that he needs to generate more profit, or to put more profit on top of the cost he gets from the manufacturing in order to cover this debt. And this is, minimum sustainable price, simply defined as the price where the manufacturer does not see any profit and does not see any losses. So it's the price where it can sustain the manufacturer in good financial way. And as you see, the last assumption is about that compressor. So we assumed it's single stage compressor, so it cannot afford 70 megapascal in this case. So either we change the design to get multi-stage compressor in order to deliver 70 megapascal, or we need to add a booster or another compressor that can increase the pressure from 420 bars to 700 bars, or even to 900 bars. So in terms of process flow, manufacturing process flow for making these compressors, as you see, we have different components inside the compressor. And a bunch of these components are made through casting, and another bunch of these components are made through hot forging. And after that, we have inspection, process, cleaning, machining, and after that, once we get that final part in terms of the shape we want and the quality we are looking for, we can assemble these parts, and then after that we can do testing for the compressor shell and internal parts before we add balance of system components. So in terms of cost curve for compressor, again, this is for the compressor shell and internal components, and this do not include, these do not include balance of system cost components. And as you see, the cost is decreasing with annual production rate for these compressors. And at the bottom of the slide, this is the, you can see the cost breakdown for two annual production rates. One is at 100 units a year, and the second one is at 500 units a year. And as I mentioned, most of the manufacturers do manufacture the shell and internal components of the compressor, and they rely on outsourcing balance of system parts. And here's a picture from BTC machines. And if you look at this picture, you see there are many components that can be added to the compressor. For example, we have some sensors, control units, motor, and other parts. So usually manufacturers rely on manufacturing major or main system, and then add balance of system parts to it. So after adding balance of system and adding profit margin to estimate minimum sustainable price, and we also added small amounts to account for shipping to United States. So as you see, here is the cost curve, and it's very similar to their manufacturing cost, but this curve is for minimum sustainable price, and you see that minimum sustainable price is decreasing with annual production rates. And at the bottom of the slide, you can see the cost breakdown at these different annual production rates. In terms of sensitivity analysis and the effect of some parameters on the final cost of the compressor, so we focused on the manufacturing phase, and we try to assess the effect of changing some parameters like capital, labor, material yield, and building cost on the final cost of the compressor. And as you see, the effect is changing with annual production rate. So we have two representative annual production rates here. We have 10 units a year and 100 units a year. And you can see that at 10 units a year production rate, we have capital cost is ranked number 1, followed by building and yield. While at 100 units a year, we have capital ranked number 1, yield, and labor in second and third place respectively. So in terms of comparative cost analysis between different countries, so we picked some of developing countries to assess the, to evaluate the manufacturing cost of compressors in these countries, and to see what is U.S. competitiveness status. So as you see, if we look at the upper part of the slide, you see it's like comparative cost analysis between different countries, and we can say that making these compressors in the United States has some advantages over other countries, except maybe for Mexican and Chinese manufacturers. And if we zoom in to look at these cost differences between U.S. and Chinese manufacturers or Mexican manufacturers, you see that major advantages for Chinese manufacturers are coming from low labor cost, low material cost, low building cost, and to a lesser extent, lower energy cost, while Mexican manufacturers have advantages relative to the U.S. manufacturers in terms of low labor cost and lower building cost. And I just wanted to highlight that I decided to keep assembly, and assembly here is assembling and integrating balance of system components into the compressor. So I decided to keep it like as individual component here, because it's really labor intensive process. Okay, moving to discuss hydrogen dispensers, and here's a picture of Tatsuno dispenser from Japan, and it shows you like a bunch of components hidden inside the dispenser. The only two components that customers can communicate with is the display and the nozzle. Other than this, I think other components are hidden inside the dispenser. So unlike hydrogen compressors, so most of integrators or developers of dispensers are depending on outsourcing these or individual components and then assemble them in-house. And here's two examples of two dispensers. First one is a single hose dispenser that's able to dispense hydrogen at 35 megapascal. And the second one is dual hose dispenser, which can dispense hydrogen at 35 megapascal and 70 megapascal. And as you see, we have about 27 different parts inside that dispenser in both cases. And the last row gives you the total part cost for these dispensers. So for 35 megapascal dispenser, the cost is around $35,000. And for dual dispenser, the cost is around $67,000 to $68,000. And in terms of the cost breakdown for parts only, as you see on the upper part of the slide, we have cost breakdown for 35 and dual dispenser. And you see that valves and meters, if they are accounted as one system, they account for about 60% of the total part cost, followed by nozzles and hoses. And what we did after that, we added other cost components like labor, capital cost, variable energy, and building cost to come up with a minimum sustainable price curve. And you can see this minimum sustainable price curve at the bottom of the slide for two dispensers. And again, the cost is decreasing with annual production rate. In terms of comparative cost analysis between different countries, and again using minimum sustainable price, you see that making these dispensers in the United States are still very competitive compared to a majority of these countries in our list, except maybe for Mexico. And again, the major advantages for Mexican manufacturers are coming from lower labor and lower building costs. Another example of manufacturing cost analysis is for heat exchanger. And in this presentation, I'm focusing on sort of advanced technology of heat exchangers. So this is for microchannel heat exchanger or compact heat exchanger. So starting with a picture of an rail hydrogen station, you see this is the size, I mean the red arrow is popping out from our heat exchanger, and you see the size of heat exchanger and relative to a dispenser and chiller just next to it. And I mean the new technology allows us to go to compact design where we can have it in size of maybe I mean 30 by 40 centimeters or even less than this, and this dispenser can be included inside the dispenser, unlike the dispenser shown in rail hydrogen station picture. So for microchannel heat exchanger, so again there are many advantages of this kind of heat exchanging technology. The first one is lower cost, and actually based on current manufacturing practices, I would say this is not the case now, but in the future we would see big cost reduction if we're going to go with this kind of technology. And another one is the size. While I mean size is not of the limitation factors in hydrogen stations, but again having a smaller heat exchanger is much better than having a larger heat exchanger. And the third and most important factor is the performance of heat exchanger. So this kind of heat exchangers proves to be more efficient than I mean plate or double tube heat exchangers. And here is the manufacturing or process flow diagram for making these heat exchangers. So starting with stainless steel 316 plates, we do some cleaning, and after that we do chemical etching or laser grooving. And then we have a quality check before we stack cold and hot plates on each other. And after that we put the whole stack inside the furnace under high temperature and pressure in order to allow for diffusion bonding between different layers. And after that we can add other parts to the stack, like nozzles and sensors or other parts we need to add. And we can do pressure testing for the whole system after we add the housing to it. So on the bottom of the slide, you see I get this picture from Heatrick, and Heatrick is a manufacturer located in the United Kingdom, and they are specialized in making microchannel heat exchangers. And as you see, the stack are, as you see, we have alternating layers of cold and hot plates stacked on top of each other. And in terms of internal structure, after hot diffusion, you see that we have sort of like good structure or solid structure between plates. In terms of plate design, as you see, here's the proposed design. So we had like two options, either to go with a parabolic channel or to go with square channel. And each one comes with its own like limitations and like advantages. But I mean, based on the discussion we had with some colleagues and some manufacturers, they believe that parabolic channel is better than square channel because it offers more heat transfer area. And this is why we chose parabolic design in our study. And in terms of the size or dimension of individual plate, as you see, the width is 30 centimeters and the length is 40 centimeters. And in terms of cost analysis, and I mean, this is the final cost analysis for microchannel heat exchanger. And again, at the x-axis we have annual production rate, and along y-axis we have minimum sustainable price. And as you see, the cost is decreasing with annual production rate. And again, I mean, we had some discussions with manufacturers, and they believe that, I mean, they have not seen any cost below maybe $20,000 or $30,000, and they suggested that we claim it's like future or the, I mean, future cost. It's not the current cost they see. So at current technology and current annual production rates, the cost is about $30,000 to $40,000 per heat exchanger. And again, I mean, in terms of comparative cost analysis between different countries, you see that U.S. manufacturers have advantages over international manufacturers, except maybe for Mexico and China. And again, I mean, Mexican manufacturers have advantages of low energy and labor and building costs. So before I jump to the conclusions slide, I just wanted to highlight the effect of reducing capital cost on hydrogen prices. So here we started with actual installation in California using first element stations, and the size of this station is I think 180. I mean, it can dispense, the capacity is 180 kilograms a day. And after that, we used our numbers or our estimates for equipment cost at two annual production rates. The first one is 10 units a year, and second one is 100 units a year, to estimate the future cost of these stations. And after that, based on the previous analysis made here at NREL, to estimate the contribution of compression, storage, and dispensing on the price or the cost of hydrogen. So we use these, ratios to estimate the effect of decreasing or reducing capital cost of different components. And we believe there is potential of 5 to 10% cost reduction in hydrogen cost using H2A estimate. So this estimate was about $5.6 per kilogram in 2015. And this number, 5 to 10% of the total cost of hydrogen, and this can be, normalized. If we're going to look at combustion storage and dispensing cost, it's about like 20% of that cost. So another suggestion or another conclusion about how we can reduce the cost of hydrogen at the pump is going with liquid hydrogen station. But again, if anyone wants to go with this decision, it doesn't come without drawbacks, because liquid hydrogen stations tend to have higher capital cost, and it's usually installed in areas where we have good number of fuel cell electric vehicles, because this kind of stations are designed to have higher capacities. And another effect on not only capital cost or equipment cost, but also can decrease the cost of hydrogen is standardization of different components. Because, for example, for compressors, there's at least 2 or 3 different technologies, including diaphragm compressor, piston compressor, and, for example, ionic compressor from Linde. So there's no standardization about different components. So we believe that going with standard design, or at least standardization by common specs for different components, should play a role in decreasing cost of hydrogen. So conclusion, we found, based on the data we analyzed, that there is sort of like inflation in cost of hydrogen stations by some manufacturers, and I would say this is because of lack of competition in the market, and because of number of installations every year is maybe less than 100. In order of 10 stations or something like this. So lack of competition in the market is one of the drawbacks of this, or getting the cost of capital cost lower. And again, lack of standardization is another factor that play a role in determining the future cost of equipment in hydrogen station. And again, based on our analysis, we found that US-based manufacturers have advantages of longer experience in the market, and we have another advantage of lower energy compared to other European and Asian countries. And in terms of future technologies and economies of scale, definitely these will have great impact on reducing the equipment cost in hydrogen station, and this should automatically reflect in decreasing prices of hydrogen at the pump. And I think that's all for today. Thanks so much.
Okay, thanks very much, Ahmad. We have a few questions from our audience.
Sure.
And the first one was on slide 12, and the question is, in the projection of hydrogen refueling stations out to 2030, is the projection for the United States only for California, or does it cover like the East Coast as well and the rest of the country?
I believe it's for California, and this is why I have a row, directed to California State.
Okay, thank you. Another question, what learning curve did you use on the unit cost calculation?
So actually, this includes learning curve. So it's beyond the scope of the study, but we believe that, for example, let us take an example of some manufacturers in Japan. For example, there are some manufacturers in Japan working with Linde from Germany, so in order to get sort of experience in the field. And we believe, again, as I mentioned, the equipment cost in Japan is, relatively speaking, 2 times the equipment cost in the United States or Europe. So we believe this should take the equipment cost down in Japan in the future. But again, we didn't use any learning curves in our analysis. This is based
Okay.
on purely on manufacturing cost analysis.
Okay, that's interesting. Thank you. Next question is how, and this questioner may be jumping ahead in terms of your analysis, but he says the question is, how does cost analysis differ if on-site electrolyzer is used instead of delivered hydrogen?
That's really good question. I mean, I don't have answer now, but I may have answer maybe, hopefully by end of this year, because I mean, now we are studying manufacturing cost of on-site production equipment. So once we finish this and add it to what we have here today, we should have like answers by that time. But now I'm so sorry, I don't have answer.
Great, thanks. Next question, can you tell us what kind of federal or state tax credits are available in the United States for station developers?
Yeah, I mean, from top of my head, I know that, I mean, California has good like incentives, and I think their program ended last year. I'm not sure they covered about like 30 to 50% of installation cost of stations in the last few years. And same thing happened in Japan. And I think their program ended last year. Again, I mean, Japan was covering, Japanese government covered 50% of the cost of hydrogen stations in Japan until 2016.
Okay. The next question, China has recently announced that they're going to be investing in fuel cell buses. Do you have a projection of the impact of China's entry into this area on the trade flow map?
Okay, so again, I mean, since it's like, I'm not sure if it's like a future plan or it's already been, I mean, deployed. But again, I mean, our maps are sort of like, we usually update them like regularly. So this is just based on the, I mean, the data we got until December 2016. But once we see like new data for China or for other countries, for sure we're gonna update our maps. But I mean, I didn't see that much infrastructure in China. So I'm not sure about like fuel cells. I know they have like ambitious plans for fuel cells, but they, my personal opinion has not yet reflected on the hydrogen infrastructure.
Okay, I think, yeah, that's why they're asking about projections. It'll be an interesting field to follow. Last question, I think, well, maybe not. Any additional heat transfer enhancement inside the microchannel?
Yeah, so the main advantages of, or the good thing with microchannel heat exchanger is if we calculate heat exchange area and relative to double tube or plate heat exchanger, it's much more. And this is why we have higher performance of microchannel heat exchangers and relative to regular heat exchangers or double tube heat exchangers. So, I mean, in terms of heat exchanging rate with time, it's really higher than double tube heat exchanger.
Oh, okay. Correction to the answer just given. California program continues through 2023. We are funding at least 100 stations. So the comment is California Station Funding Grant Program has not stopped.
Okay, that's good. Good news to hear.
Yeah. Let's see. So next question, when computing the cost of hydrogen, dollars per kilogram, what amortization rate is used for a capital investment?
So again, I relied on a previous study by Unreal. So to be honest, I don't remember the number, but I think it's around like 10 years, if I'm not mistaken.
Okay.
Yeah. So because I used like the ratios from this study, it was focusing on compression storage and dispensing cost.
Okay. Next question, did you assume the building and land cost for only the footprint for a typical retail outlet?
So our assumption for building cost is based on the production line multiplied by a certain factor. So this, this assumption accounts for the manufacturing facility itself. Does not include like parking lot, cafeteria, and maybe other like adjacent facilities.
Okay.
Because we looked at direct manufacturing costs, and these or other indirect cost components should be accounted for in a minimum sustainable price.
Okay, that's all the questions I see. Chris Worth, can I transfer this back to you?
Yeah, Nancy, I just had one more come in I can toss out there before we wrap up as well. The question is the cost of Pennsylvania hydrogen station operation available? Is there any kind of localized information available?
I think so. So if you want, I can send it like offline. But by the way, Pennsylvania and Ohio, there is a good hub of manufacturers, and there's, I think, in the East Coast, there's a new plan to have more hydrogen stations along the East Coast. But
is there any is there any public available sources for information like that, or is that something the questioner could maybe email you directly about?
I'm gonna send you what I have for East Coast, not only Pennsylvania. And I think FCTO is funding other projects that cover East Coast, like Virginia Clean Cities and Ohio Coalition, I think. Nancy knows more than I know.
Okay. How would the questioner find out the answer?
It sounds like something we could follow up with after the webinar.
Sure.
Okay.
Sure.
Yeah, that's all the questions I see here. If there's any closing comments from Nancy or Ahmad, we'll have those now.
Thanks everybody, and keep the faith.
Yeah, I really appreciate the opportunity you gave me to cover this topic. I think it's an important topic. And again, if anyone is interested in getting more information about our work, my email is on the last slide, so feel free to shoot me an email directly, or you can visit our website, www.manufacturingcleanenergy.org, where it covers this analysis and other clean energy manufacturing analyses for technologies like solar, wind, geothermal, and other technologies.
All right, Ahmad, if you would go to that last slide for me, please. Big thank you again to Dr. Ahmad Mayas for a thoughtful and informative presentation, and also thank you to Dr. Nancy Garland for hosting today's webinar. That's going to conclude our presentation webinar today. If we didn't get to your question, again, please feel free to email the presenter directly, and they will try and respond in a timely manner. I'd like to thank everyone for joining in and remind you that the webinar and slides will be available online in about 10 days at the hydrogenandfuelcells.energy.gov website shown. The webinar recordings are under the Information Resources section. I will also include a link for the webinar slides in a follow-up email that comes out of the GoToWebinar system here. Encourage everyone to sign up for our monthly newsletter, which includes information and registration for upcoming webinars. And you can find that at the Hydrogen and Fuel Cells Energy Gov website there as well. Have a great rest of your week, everyone. Goodbye.
Bye.